Hi class, we're on to the next section, chapter 2.4. Today we're going to talk about asymptotes and holes. Now we've talked about this stuff a little bit before in chapter 1.6. However, that section was referring to things solely on rational functions. This is going to apply to more than just rational functions. However, we are going to use rational functions to demonstrate the ideas that we are discussing in this section. So a lot of the ideas that we're talking about now are the same as those in 1.6. However, we're going to be using the limit notation in order to describe our functions and what it is that they're doing around these points. Okay. The limit for a hole in a graph exists. Okay. So if you remember what a hole is literally your continuous graph, right, or a continuous portion of a graph, but just one point taken out. Okay, we call it a removable discontinuity, because if we were to put the point back in, then our function would then be continuous. Okay, so the left side limit at the hole and the right side limit at the hole are both approaching the same value. It's just that our function isn't defined at that point, right? So the limit exists there because the left and right side limits agree with each other. But my function is not defined at that point. We can't evaluate it at that value because it's undefined. There's no hole there, okay? So when we have a hole at the point that we're trying to evaluate our limit, then we have to use other algebraic means to work around the hole, basically. Okay, so basically what we're going to do is we would simplify our function. Okay, so our goal is to eliminate our problem term from our denominator, or to use the squeeze term. So sometimes we can find a function that's always larger and another function that's always less than the function of interest to us that has the same limit at that point, and then we could just use the squeeze term to say, hey, this is what the limit is because this function and this function both also go to this value at that point. Vertical asymptotes are a little bit different. So in chapter 1.6, what I had you guys do when we had a vertical asymptote was we looked at the next closest zero, either on the left or the right, and then to evaluate our function in between our vertical asymptote and that zero. And if our function was positive, then it was always positive as it approached the asymptote, and it would just continue to get larger and larger and larger because there's no more zeros, right, in between that point and the asymptote. So there's no chance for our function to cross the axis again, right? So it has to just get bigger and bigger and bigger. Same thing as if it was negative in between the zero and the asymptote, then it stays negative and it goes to negative infinity. So we pretty much do the same thing here. We're just using a different notation, but the idea is the same. We just look at the sign and we say, well, it has to go into infinity or it has to go to negative infinity because it never comes across the x-axis again. Now, typically what we say is that the limit, even if the limit, let me rephrase this, even if the left side approach for a vertical asymptote goes to infinity, and the right side approach goes to infinity also, we would say that the limit goes to infinity, but we also say it doesn't exist because infinity is not a number. Okay, but typically when we're doing math and we're portraying this information to somebody, we would say the limit goes to infinity, right? But technically the limit does not exist because infinity is not a value. But we say infinity or negative infinity because it portrays to the reader that that is what our function does at this point. All right, so this is basically me repeating myself. And so horizontal asymptotes. So horizontal asymptotes work the same way. It's the long run behavior. So we've talked about this in the section for polynomials. We talked about the end behavior of our polynomial based on the degree of the polynomial, right? Odd degree polynomials do this and even degree polynomials do that. We also talked about long run behavior for rational functions when we have a polynomial over a polynomial in chapter 1.6. We stated that we look at the difference of the degrees of the polynomial, and the difference is basically, the difference in the degrees of the polynomials in the rational function, I should say. And the difference in the degrees is the value for the polynomial that the rational function behaves like in the end behavior. So for instance, if the difference between the numerator polynomial and denominator polynomial is 5, then my rational function acts like a 5th degree polynomial in the long run behavior wise. Okay, so we're really doing the same sort of thing, except for now we're looking at we're using the value of limits. We're using limits instead to portray that same information, and we're going to have things at infinity where we're no longer just talking about rational functions, right? We could be talking about the long run behavior of sine over x divided by x, right? So we can talk about different functions now in their long run behavior, not just asymptotes, or I'm sorry, not just rational functions. There's a couple of problems that do pop up when we're talking about horizontal asymptotes, sometimes vertical asymptotes too, and those are discussed in greater detail in chapter 5.5. So let's see, we're just looking at long-term behaviors, right? So like I said in chapter 1.6, we kind of want to know what dominates, right? If it is a rational function, does the numerator dominate or does the denominator dominate? Maybe I'm adding two functions together. Which one of these functions gets larger faster or smaller faster if I'm plugging in very large values or very large negative values, okay? So as my x's go to infinity or negative infinity. All right, so let's take an example. So this is a familiar problem. We've used this for the 3rd time now. I used this in chapter 1.6, and we just used it in the last video for continuity. So we know what this looks like. We know what this looks like when we factor it, because we factored it a few times. In the last section, we took the limit as x goes to 5, which was fine because 5 was a continuous point for our function. Now we're looking at what happens when x goes to -1. So x equals -1 is not a continuous point in our function. So in order to figure that out, we want to factor everything so we know when I'm continuous and when I'm not. Okay, so we're being asked to evaluate. So basically it just says factor everything. So this is the factored form. Okay, x equals -1 is a whole because there is a factor in the numerator and a factor in the denominator that both have this as a 0, which means it is not a vertical asymptote, but that it is a whole, right? So if I want to look at the limit here, the easiest thing to do is to algebraically eliminate those two common factors, right? The factor in the numerator and factor in the denominator. The long way to go about this would be to plug in several values and see what's happening when I come from the left, and plug in several values and see what's happening as I come from the right, and see if those things approach the same value, which they should, because as I said before, for a whole, the left and right limits are going to agree. There's just a single point in our graph that basically has just kind of been erased when we have a whole. So algebraically, just eliminate those common terms, and then now I have an equivalent form, right? This form is equivalent to this, and this equivalent form, which gives me all the same values out, is continuous at this point. So I've algebraically manipulated this equation to now be continuous over this interval, so then I can just plug in that point, right? So remember, if our function is continuous, we can just plug in our values. So this is going to give me -6/4, which is the same as -3/2. So the limit as I come towards -1 is -3/2. Okay. So even though I'm not continuous at this point, my left and right limits do agree, so I do have a limit. So let's look at our other zero. So we're looking at our factored form here. So we looked at what happens at -1. So what about this vertical asymptote of x equals 1? So for a vertical asymptote, I can't really manipulate this rational function so that it's continuous at this point. So if I want to talk about the vertical asymptote, I have to talk about what's happening as I approach from the left and as I'm approaching from the right. Okay, so I have to look at these two limits separately since I have an asymptote. Because one will go to infinity or negative infinity, and the other will also go to infinity or negative infinity. They don't typically have to agree, but they can. But it's very possible that they go to different levels of infinity, right? So I know that this is a vertical asymptote. So we need to check, just like before, the sign of a value between 1 and the closest 0. So the zeros are -2, 2. We get that from the numerator, right? Because this does not count as a 0, this is a whole. So the zeros are, okay, -2, +2, and vertical asymptote of 1. So I want to talk about what happens between that. So if I'm looking to the left, I'm looking at a value between -2 and +1. The easiest value to look at is the value x equals 0. Okay. All right, these values check is x equals 0. Sometimes, if we're sharp enough, we can just think about all values in between -2 and 1, and we don't have to check a very specific value. But if we have a nice easy value, then it is easy to check a specific value. So we're going to do that. We're just going to plug in 0 everywhere. We'll get a positive, a negative, 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 positive. So sign-wise, that looks like this, right? Negative on top, positive on bottom, which means overall I have a negative value. So after my last 0, as I approach my asymptote from the left side, my function is negative, which means it will always be negative. And since I cannot plug in my asymptote, I know it goes to plus or negative infinity. It never crosses the axis again, so it goes on to be negative forever and ever and ever, which means it goes to negative infinity. Okay, so the limit as I approach 1 from the left, or the negative side, is going to be negative infinity. So I'm going to do the same thing from the positive side. So I need to look in between 1 and 2 and look at what happens to my signs. Okay, so I'm going to look at every x value in this interval. So if I'm in between 1 and 2, I'm positive. Positive plus positive, positive plus positive. Here my values are all less than 2. So I'm taking something less than 2 and subtracting 2. So this is negative. So I got plus, plus, minus. Here, these are all larger than 1, so this will be plus, plus, and plus. So I have all pluses and a negative, and everything on the bottom is also positive, which means overall, I have a negative value. So the limit as I come from the right, okay, this way, will also approach negative infinity. Okay, so as I come from the positive side. So as I come from the negative side, and as I come from the negative side, my limit goes to negative infinity. So that does not mean, okay, this does not mean that my limit as x goes to 1 is negative infinity. Okay, the limit as I approach from the left is negative infinity. The limit as I approach from the right is negative infinity. But since it is a vertical asymptote, there is no limit at that value. I can only talk about the left-hand limit and the right-hand limit. Even though they agree, that does not mean that the limit as x goes to 1 is negative infinity. It does not work that way. Okay, so I can only, for vertical asymptotes, I can only talk about what's happening from the left and from the right, not at that point. Okay, I just really wanted to make that very clear to you guys. So the next thing that we're going to do is we're going to look at the horizontal asymptotes. Okay, so the limit as x goes to negative infinity and the limit as x goes to infinity. So what happens in the long run behavior, the end behavior, when I plug in very, very large positive values and very, very large negative values? What is my function doing? So we already know from looking at this graph before that since the degree of the lead terms are the same, that it's just a ratio, because x cubed gets larger way, way, way faster than all of these things, right? X cubed grows faster than just an x. X cubed grows faster than an x squared. Same thing on the bottom, right? Both of these x cubes grow at the same rate, and they outgrow these other terms very, very quickly, right? But I basically have an x cubed over another x cubed, so I just look at the ratios of their leading terms. So the end behavior for both of these is just 2. Now, that's nice for polynomials. It's easy to see that kind of thing, right? If I had just an x on the bottom, I would know that this grows way, way, way larger than just an x in the denominator, so everything goes to infinity, right? But again, this doesn't always happen. Sometimes we don't always just have polynomials over polynomials. So we want to be able to learn how to deal with this. There's another way that's more algebraic for dealing with rational functions like this and their limits at the end behavior, which we'll go over right now. It's always nice to have an algebraic means of calculating stuff. Although understanding when we're talking about large values, we're talking about domination. Which part dominates everything else? Which grows faster than everything else? Okay. So an algebraic method of doing this would be, so let's summarize first before we go over this, right? So the limit as I go to -1 is -3/2. The limit as I approach 1 from the left and 1 from the right is -infinity. And so this is my graph, right? We've seen this graph a few times now, but notice now that I have my asymptote, and as I approach from the right, I go to -infinity. As I approach from the left, I have -infinity. When I approach my hole here, I go to -1.5. Okay, -1.5. Because the left side and the right side limits both agree, they both go to the same point. There's just a spot here that doesn't exist. Okay. My long run behavior, I approach 2. My long run behavior, I approach 2. Let's move on to our next example. So we're going to find the limit as x goes to 0 of square root t squared plus 9 minus 3 over t squared. So very, very obvious that x goes to 0 makes the denominator 0, which is not allowed. It's not very clear how to algebraically manipulate this so that we don't have a t squared in the denominator, right? So we could take the left and right hand limits of this by plugging in several values as we get closer and closer to 0, but we do have some algebraic means actually of manipulating this. So what we would want to do here is we would want to rationalize the numerator, right? So normally we rationalize the denominator when we see a square root in the denominator. So we're actually going to do the opposite. We're going to unrationalize the denominator, meaning we're going to make the numerator have a whole number, or a non-square root term, I should say, and the denominator will then contain a square root term. So in order to do that, we're going to multiply by the radical conjugate, top and bottom, in order to get rid of the square root sign that we have in the top. So I'm going to take this and I'm going to multiply it times 1. Okay. And what I'm going to multiply by is the same numerator, but with a different sign in the middle. Okay. So then it becomes a difference of squares. So I'll multiply this whole thing times square root t squared plus 9 plus 3 and this as well. So difference of squares will give me t squared plus 9 minus 9 because it's a difference of squares. Okay. The denominator is just t squared times square root t squared plus 9 plus 3. The 9's cancel out. Now I have a t squared on top, a t squared on bottom, and guess what? I get to cancel those out, right? So now I have a square root 9 on bottom plus 3, which is 1 over 3 plus 3, or 1/6. So sometimes we have to be really, really crafty when we're approaching problems like this, right? So if we have a radical, definitely try to rationalize the numerator or rationalize the denominator, whichever one seems appropriate. If you have a rational function, then you want to try to simplify it as much as possible. See if you can cancel out some of those zeros. Okay, so let's take another example of a rational function. Here I'm looking at what happens as I go to infinity, so the long-term behavior to the right of this polynomial over this polynomial, right? So you see I threw a pi in here just to mix it up a little bit. Remember, pi is just a constant, so it's just a constant term. I can notice that x over 4 dominates the numerator, x squared dominates the denominator. So I know that the long run behavior, this really acts like an x squared function. Okay, I know x squares go off to infinity. So using our knowledge from 1.6 about rational functions, about what dominates what happens when you have, polynomial over another polynomial, I know that the difference is a square. So, if I divide this by this, it's basically x squared. So I know that this should go off to infinity. Okay, so we can tell by looking at the domination principle, right? Which is nice, it's easy, it's conceptual. But it's also nice to know how to do this algebraically. So I know I talked about this a couple of slides ago and then I never actually did it. It's because I got ahead of myself. So here we're going to talk about how to algebraically figure out how we can evaluate these things at infinity. Remember, this is for infinity. This is not for x equals 7, for instance. Okay. So if I have something that's not very clear, or I'm still just not understanding this idea about this grows faster than that, so this is the way that it acts, we can use our methods of algebra. Okay. So again, here, this is just me explaining again that looking at the dominating terms, x4 and x squared, if you divide those, is basically an x squared term, so it acts like x squared. Okay. So if I want to do this algebraically, then what we're going to do is we're going to look in the denominator, right? And we're going to find what grows the fastest there. In this case, it's the x squared term. And what I'm going to do is I'm going to divide everything present by x squared. So this, everything by x squared. And so it's okay for me to do that because I'm being even, I'm being equal to everything present. So I'm not changing the value of anything. I'm just going to make it look like something that's easier for me to evaluate, right? So I'm going to divide everything by x squared, and I'm going to look at each term separately and look at what happens as x goes to infinity. So we're going to use that property of limits, some of those ideas from the properties of limits section, in order to do this. So we're going to look at this basically as the limit of the numerator, limit of the denominator. We're going to be looking at each term separately and what it's doing as x goes to infinity. Okay, so we're going to take everything, divide everything by x squared. So I have 3 x4 over x squared, 5x squared over x squared over x squared over x squared, everything over x squared. Okay, so it looks like this now. And now if I look at what's happening as x goes to infinity, I look at everything. Anything with an x in the denominator is going to go to 0. This is going to go to 0, this is going to go to 0, this is going to go to 0, this is going to go to 0. So what's going to happen is this is all going to look like 3x squared minus 5 over 1. Because if I look at the individual terms, right, looking at properties of limits, I look at the limit of the numerator, limit of the denominator, the limit of the numerator, I can look at each piece as I get large. Okay, so 1 over x goes to 0. Anything over x squared also goes to 0. So this thing, what I started with, goes to 3x squared minus 5. It goes to exactly what I said it would. It acts like a quadratic. Okay, specifically this quadratic. So what does this do as I get very, very large? I get larger and larger and larger. So I go to infinity. So this is a nice algebraic way of looking at limits at infinity. Now, if I was going to negative infinity, I would do the same thing, but say, okay, what happens when I plug in very large negative values? In this case, it's a quadratic, so it would still be positive infinity. So let's go ahead and do another example. So let's look at sine of x over x when x gets very, very large. So we have to kind of think about it, right? Here, we can divide everything by x, which probably is not going to be super helpful because we kind of will come up with the same thing. But we can talk about what is going to dominate. Well, sine of x does the same thing. It oscillates. It's a wave function. What does x do? X just gets larger and larger and larger and larger. So while this is oscillating, the denominator is getting very, very large, which means overall, this entire thing is getting very, very small, right? When I divide things by large numbers, it's actually really small. 1 over a million is a very small amount. So what we're going to do here, though, instead of just looking at how this dominates, is we are going to use the squeeze theorem. Okay, I know that sine stays in between -1 and 1. As I said before, it oscillates. It's an oscillating function. Okay, so if I divide everything by x, okay, right, divide everything by x, well, what is the limit of 1 over x? The limit of -1 over x is 0, okay, which is the same as 1 over x when I plug in very large values. So this function, my function, is squeezed between two separate functions that both go to 0. Okay, so since the limit of both of these functions go to 0, my function here has to go to 0, which I said in the beginning conceptually, because I know that this oscillates and this gets very, very large, right? So it starts to get very small overall, which means it goes to 0. So instead of looking at this conceptually, we decided to show this using the squeeze theorem, right? So I bounded my numerator, then I manipulated those bounds so that it looks like my function, divide everything by x. Negative 1 over x and 1 over x go to the exact same value when you go and plug in very, very large values, which means the function in the middle, my function, has to also go to that limit. Okay, so the linear denominator dominates my oscillating values of the numerator for large values. Okay. Okay, so let's go ahead and look at this graphically. So we have 1 over x and we have negative 1 over x. Let's change this color to red. Okay, and then if we kind of zoom in a little bit and let's look at our function sine of x over x, we can see here that it's bounded in between those functions. Okay, and since my functions, right, so it oscillates and it stays within those bounds. Sometimes it's equal, and that's fine, but it never is larger than 1 over x or negative 1 over x. And as I come out to the very large values, right, it always stays within those bounds and oscillates between those, and it just gets smaller and smaller and smaller. It doesn't reach infinity, but it goes to infinity. That's the limit of that function.